Welcome to Haltech Elite NSP Training Part 28. In this training tutorial, we're going to be exploring using alternate load inputs for things like our speed density table. So how we can change out something like manifold pressure to something like throttle position or engine pressure ratio. There's a lot of options. We're going to talk about how all of these work within this training module. Without further wait, let's jump in so we can check this out.
Okay, so let's get started. We're going to be taking a look at working with our alternate load inputs that we can utilize in our speed density volumetric efficiency airflow model. Now, we've talked about pretty extensively here our speed density airflow model. We know we have an underlying equation, fuel mass is equal to air mass divided by target air fuel. So if we can figure out what the air mass is being ingested in the engine is going to be, and then we know what the target air fuel is going to be, we know how much fuel mass we need to deliver into the engine, and by knowing things like our injector slope, our injector dead time, and our short pulse width, we can get a final corrected injector pulse width that we pulse at the injector to deliver the fuel mass relative to the specific injector flow rate and size that we're dealing with. Now, if we have everything sorted out in terms of our fuel modeling and our airflow modeling side of things, the equation will balance, and essentially we're going to hit the target air fuel that we're requesting. So we like to always have both the fuel model and the airflow model dialed in properly. And we've talked about how to deal with bad injector data, how to tell if the values in our table here are accurate in the speed density model, understanding how all of the injector data plays a role in going in and changing that fuel mass to injector pulse width. So we've went through everything pretty extensively. Now I'm going to introduce the concept for this tutorial, taking a look at this parameter up top here called fuel load. Fuel load can be changed to something other than manifold pressure. So right now our table here is based on our map pressure reading. We know that when we're talking about the speed density airflow model, that the air mass is an estimation of airflow entering the engine. It's not actually directly measuring the airflow, and we're doing this estimation based on knowing our map pressure, based on knowing our volume per cylinder, which is displacement number of cylinders, also based on our air density, which is going to be a factor of the air temp, charge temp reading. So if we plug all that into the equation, and then we also specify the VE percentage here, that's going to give us the actual airflow or air mass estimation, how much air mass is entering the engine. This would be the exact equivalent if we had a mass airflow sensor and we were directly measuring the amount of airflow or air mass from that MAF sensor. So instead of measuring it, we're estimating it. This is better for a performance application in most cases, running a speed density map pressure based system rather than a mass airflow sensor. Although that has its own advantages, we'll be taking a look at having a specific tutorial talking about the advantages and working within the MAF tuning within our Haltech Elites, but it's not as commonly found as our speed density volumetric efficiency model here. Now, we're going to find here that, again, our table, in our VE table here, is based on engine speed, also based on this fuel load, which is set to map pressure currently. We're going to find that it looks up in the breakpoint scaling here. So looking at our breakpoints, it looks up what that manifold pressure is going to be. It looks up what the engine speed is going to be. And then it tracks to where the percentage of VE is going to show here, the percentage of cylinder filling. So all it gets put into the equation. Now, what's going to happen here if we have a situation where we have a big throttle body or huge camshafts that pull very poor engine vacuum? Right now we're showing about 19, 20 inches of vacuum. We might have a cam that pulls something like -5 to -3 inches of vacuum. We'll find as we're driving around, we really only have this much resolution. Let's say between -8 to 0. We only have this much resolution in our table to deliver the proper airflow model and fueling to the engine, which is really going to produce an inconsistent fueling result and ultimately an engine that doesn't run very smooth. So we might have a problem with usable resolution because the camshaft profile or the throttle blade is so large that if we tip the throttle blade open, we go from reasonable vacuum to 0 PSI almost instantly. So there's no real usable resolution in the table. Or we might find that we have a combination of ITBs and a big camshaft where we pull very poor vacuum, and we also have, as soon as we give it any throttle blade input, we're pretty much at atmospheric or 0 PSI level here. So we have very little usable range. We might not have this much range instead of this much range to map out for idle and part throttle vacuum conditions, but it can be a huge problem. Well, in that situation, we want to tune in something called alpha N, and we can switch over our fuel load type instead of map pressure to something like throttle position, which allows us to have a direct input for the throttle blade movement to look up our percentage of cylinder filling. We'll talk about how we can switch that here in a little bit. And we also have another variable here that we can account for that, let's just say we're not tuning alpha end based. We don't have a huge throttle body. We don't have ITBs or a massive cam that...
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here. And you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.